Last time I talked about this transformer from the colder sign that has an always on and a flashing portion. The flashing was not working. I said it had a mechanical motor that operates a little switch to do the flashing, and I found out I lied because older models did that. This one already had a circuit board. This is the circuit board, and I did a visual inspection and found that this capacitor has cried a tear. So I reverse engineered it. There's not much on it really. So there's a chip well known in electronics, the NE555, probably the most common timing and flashing chip ever made. And this one is a 556, which is just two 555s in one package. Then we have a triac here that's obviously switching the AC load, so it's like a special transistor for switching AC loads. And the 555 needs a small DC voltage, like 5 to 15 volts DC to operate. And in the 90s when they built this, you could have used a regular transformer, little transformer, rectifier and capacitor to make the low voltage DC. Or if you wanted dirt cheap, you could build a capacitor dropper. And obviously the transformer said, yeah, dirt cheap is just right for our customers. So they built a capacitor dropper instead of the transformers. Capacitors will act like a special resistor when powered with AC, so they limit the current into the circuit. And I've drawn the circuit out here. So we have the two AC poles coming in and the earth going to the case and the sine frame. One AC pole is going through our switch and then directly to the black wire into the potting. The black wire is the common for the both neon transformers, and then we have a blue for AC power for the steady on and a red AC power for the flashing transformer. After they go through the switch, they go through these two blue capacitors, which do the capacitor dropper current limiting, and they go in between those two diodes here to make a little rectifier and to get a low voltage DC with a positive and a negative rail. Then they put a Zener diode, which is like a special diode to limit voltage to a certain value. So they decided for 12 volt here. So from here on we have 12 volt DC on this rail and the associated 0 volt DC on this rail. At the same time, the plus 12 volt is still one of the AC hot poles. So that's a bit difficult to understand. We'll just watch it from here now. They put an electrolytic capacitor to smoothen the 12 volt DC. Then this is the 555 flasher circuit. It needs some discrete components around that I have not drawn here, just to show it simpler. So it operates on 12 and 0 volts. It has a flashing output that operates this triac that I showed as a switch here, and then we have the flashing power going to the flashing transformer. So although we have really 12 volts DC here, you cannot touch this because you will still touch the AC poles can be inverted. Some countries don't have polarized power plugs. So you could not use this for like a model railway or anything where you could touch the low voltage DC. Capacitor droppers are really only suitable for low voltage circuits that are fully enclosed and don't have any interface with a person. Okay, so I measured these two capacitors. One measures the value that it should have, the other measures high ohm and no capacity, so it burned open. And I thought, well, what path did the current take to burn this open? So it must have shorted one of the capacitors, and then a high current must have traveled here and through this diode back to the other AC pole. Although these two measure fine, I replaced them just for good measure. I'll also replace the Zener diode and the electrolytic cap because it is 30 years old and electrolytic caps are just a wear part. So I'm going to exchange these parts now. I have tested the transformers individually by directly feeding power in here and they work. So I can't test the NE555 except in operation. I'll just replace the capacitors and the other parts that I said now. If it works, it's all right. If it doesn't, I'll throw it away. Okay, I'm about to plug this in. Will there be flames? 3, 2, 1. That looks about right. Yeah, that should be fine. Let's measure this DC control voltage in circuit. Yeah, 12 volt, it's working. And that's another flaw of this cheap dropper capacitor and Zener diode circuit. If this diode fails open or there is an interruption, we won't have a DC voltage limit anymore. So the DC voltage will go up and damage our capacitor and the chip. So as I said, it's really the most cheap short version you could do. Alright, I'll put this back together and then we're good. Thanks for watching. See you soon.